This is the final piece to the Plant Biosecurity Project, CRC 1015. It is the economic analysis of a return to cereal pre-breeding for exotic pests and diseases. Investment in pre-breeding is risky, and throughout this presentation I will explain why. For clarification purposes, pre-breeding refers to the preliminary work of plant breeding research before cultivar development, testing and release of the resistant variety. You can think of this as having all the prep work done before the pest arrives in readiness. Put more simply, if we invest in pre-breeding, we can have a resistant variety available within 5 years after an incursion. Without pre-breeding, we could be waiting for 10 years or more before a resistant variety is available. Therefore, the benefits or returns to investment come from reducing the delay between the arrival of the pest and the arrival of the resistant variety. And these benefits, or this delay, translates into yield losses, chemical costs, and for some of these pests, price discounts. But just going and developing breeding lines for wheat and barley for these specific pests does not generate a return until that pest arrives in Australia. And the value of those returns depends upon the pest establishing and its spread and damage throughout the cereal growing regions. And even if these factors were certain, the returns are limited to the delay between having a resistant variety without any prior pre-breeding, the availability and costs of chemical options and alternative management options, and the actual adoption rate of the resistant variety itself. For cereal breeders, it's also a really risky investment in this early stage. The reason being, there is only a short-term competitive advantage for those that release the first resistant variety due to genetic spillover which happens in this industry. Resistant varieties are rarely adopted in that initial phase, and the breeders can't be sure of when they will actually be releasing this resistant variety. And only a fraction of the benefits are captured by the breeders in endpoint royalties. So therefore for them, it may actually be more profitable for them to just wait until the incursion occurs and the pest establishes before taking action. Therefore, industry funding is required for industry benefits. We have addressed 3 important questions. What is the return to this investment? Which pest gives the highest return to investment? And how should we prioritise investment? We've estimated the value of return for 6 high-priority cereal pests and diseases: carnal bunt, Russian wheat aphid, sun pest, exotic wheat stem rust, Hessian fly, and barley stripe rust. Here we have the pest suitability of Australia for these 6 pests. We've based these predictions on climate suitability modelling. For carnal bunt, we used the heat thermal index. We used Climax using individual pest parameters for wheat stem rust and Russian wheat aphid. We used climate matching for Hessian fly and sun pest. For barley stripe rust, we assumed the same distribution as wheat stem rust. Damage and persistence can be expected from the bands with the red arrow upwards. We wanted to avoid over or underestimating the impact of these pests across Australia. We didn't want to say the pest will be everywhere and is going to cause the same amount of damage across Australia. So we disaggregated across Australia by disaggregating 195 Bureau of Statistics statistical areas. We combined that spatially with production, land use, and the pest suitability. And what this did was it allowed us to assess the impact in each statistical area. Ranked highest to lowest for mean return to investment is exotic wheat stem rust, Russian wheat aphid, barley stripe rust, sun pest, Hessian fly, and kernel bunt. We developed an investment return model and used both economic and pest parameters. The results are based on 1,000 Monte Carlo simulations with random incursions and the spread related to the pest suitability over 50 years at a 5% discount rate. We also did an extensive sensitivity analysis. We did this for each pest. We had a set of restrictive assumptions about how the producers could adapt to these pests. They could do nothing, they could use sprays when economically feasible, or they could adopt a resistant variety when available. The first three have a significant return to investment. The reasons being they have a high probability of arrival, they have a significant yield effect, and they're also very rapid at spreading. The last three do not provide a viable return to investment. The reason being they have smaller erratic yield effects, they are very slow spreading, and the biosecurity or trade issues surrounding those pests are not addressed by a resistant variety. The high coefficient of variation also indicates that this is highly variable. In all cases, the modal returns were equal to 0. This is further evidence that this is a risky investment and extremely high level of uncertainty relating to these returns, even though these three pests, on average, give a viable return. Stochastic dominance is an alternative method of selecting between investments. It accounts for the full distribution of returns, and second-order stochastic dominance suits a risk-averse investor. As you can see here, exotic wheat stem rust has dominance over all other pests. Kernel bunt, on the other hand, shows no dominance at all over any other pest. Russian wheat aphid, which actually was the second highest in returns, dominates Hessian fly and sunpest, but does not dominate barley stripe rust. The reason being it has more returns equal to 0. Another part of our analysis had to be, if there's going to be a delay in the resistant variety, how is that going to impact on chemical demand? These results are based on an initial incursion of 100 hectares and our model. And as you can see, the exotic wheat stem rust, Russian wheat aphid and barley stripe rust have the most demand on the chemicals. The yield effect for kernel bunt was always too small to ever cover the costs of using chemicals and therefore not feasible. And for Hessian fly, insecticides are seldom justified because delaying planting is actually a more effective control method. In terms of challenges and issues arising from our research, knowing the yield losses is key to determining the investment return. And predicting the behaviour of these 6 pests that have not arrived in Australia yet was difficult. So what we did, we resorted to a range of yield losses recorded from around the world in the literature. We produced a probability density function for proportional yield losses. We assumed that the modal yield loss was the mode in a perfectly suitable area for these pests, and the shape aligned with the frequency of those losses. For Russian wheat aphid, we couldn't be sure of the frequency of the losses, so we had an even distribution up to 82.9%. For Hessian fly, we had a range of 2% yield loss up to 15%, with the mode at 7.5%. Barley stripe rust could go up to 50% yield losses, but it was generally sitting around the 0.1% yield loss. So for any area where the pest suitability was less than 100%, we adjusted the distribution and we scaled it down, similar to what's shown here for exotic wheat stem rust. And for the statistical area, we would draw a random yield loss in each of the 50 years for the statistical area. And this was applied to the yields of that particular statistical area. This was a method of overcoming uncertainty. It avoided using a single rate of yield loss, and it allowed for an upper bound for epidemic years that may occur. We had a similar dilemma when trying to estimate the annual dispersal distance that these pests could spread. We weighted the distance, allowing for jump events that may occur. This is a really good representation of the pests and how their biology can affect their spread and give us time to respond. So Hessian fly and some pests are really quite slow at spreading, whereas we really need to be concerned about the stem rust and the Russian wheat aphid and the stripe rust because they can shift in the wind. This sort of data is really critical when modelling studies of regional impact. And improvements in these estimates would help industry immensely to prioritise research efforts and pest risk. We feel that this research will help GRDC and breeders to prioritise research projects and investment. We also anticipate this research will be valuable to organisations involved in assessing returns to biosecurity research and development. The beneficiaries are cereal breeders and researchers involved in pre-breeding, farmers and the cereal industry in general. In conclusion, understandably, investing in pre-breeding when we don't know the pest is going to arrive or when it will arrive or if it will like it here is risky. But given our estimated values of returns, we see a case for moderate level investment in exotic wheat stem rust, Russian wheat aphid and barley stripe rust. Our further recommendations are about ensuring that Australia has the capacity to respond to these pests and regularly assess the risks. We also feel it is really important that Australia keeps its strong collaboration with international breeders. Thank you. Ian. Are we doing questions, Cheryl?
So is this based on the assumption that we really don't know, like, when each one of them is going to arrive?
No.
But is there actual some indication of probability of which one of them is going to arrive first?
Some of the prior work analysed the likelihood and probability of arrival. So it ranges from 1 in 10 years right up to 1 in 100 years.
And it varies for each type of pest?
Yeah. So that was used within the model as well. I've bamboozled you.
Just wonder about the choice of discount rate of 5%.
Mm-hmm.
How did you arrive at that?
Ben arrived at that 2 years ago when the rate was higher. And we haven't adjusted. But in our sensitivity analysis, we did move it. And it does have a little bit of effect.